Hi guys, this is John Hashmat and welcome to Physics Simply.
In this video, we'll be seeing the effects of current on the magnetic field or the magnetic fields produced by a current. In front of you, we have a solenoid and some compasses here to show the direction of the magnetic field. Now there is no current in this solenoid and all the compasses are pointing due north, which is in this direction. But once I switch on a current and increase the voltage, you can see the stronger the field becomes, the more the compasses take another direction. So for example here, these compasses are pointing inwards toward this side of the solenoid, and these three compasses are pointing outwards, away from the solenoid. Here the field is pointing in this direction, here the field is pointing in that direction. If I increase the current, I can make the field stronger. If I switch off the current, now the compasses take their original direction, which is due north, which is the north of the Earth. Now you can see that I've reversed the polarity of the potential difference across the solenoid, so the current would be circling in an opposite direction to the previous one. Now if I switch on the current again, the compasses which were pointing towards the solenoid are now pointing away from the solenoid, and these compasses have reversed their direction. They were pointing to the left, now they are pointing to the right, and these compasses are pointing inwards towards this side instead of outwards. So when I reverse the current in the solenoid, I reverse the direction of the magnetic field lines or the flux lines.
A magnetic field is a region where a magnetic material would experience a force, a magnetic material like iron, steel, cobalt, or nickel. And it's also a region where a charged moving particle will experience a force. That means a current inside a conductor, or just an electron moving, or any charged particle moving inside this field, it will experience a force. And the force is defined to be moving away from North Pole, like so, and towards the south. That's the direction of the magnetic field. It's defined as to be out of a North Pole and into a South Pole. But that's a simple type of field. That's field around a bar magnet. So you know North Pole where it is and where is the South Pole, and you can just draw a simple direction. But what if you have a current, a wire carrying a current? It also creates a magnetic field around it. So the way to know the direction of the magnetic field is using the right hand grip rule, and it's used as follows. If you have a straight wire, then you would point with your right hand thumb in the direction of the current in the straight wire, and your fingers will curl in the direction of the magnetic field. So this is the current, and we'll call the magnetic field B for now. So for a straight wire, the thumb of the right hand points in the direction of the current, and the fingers curl around in the direction of the magnetic field, which means that the magnetic field will be a circular field or a curved field. If you're dealing with a coil or a solenoid, the wire is curled around, so the current is a circular part. So your fingers will point in the direction of the current, and your thumb will be pointing in the direction of the field, so it would be somehow straight. The magnetic field will be somehow straight inside a solenoid or a coil. So how to use the right hand grip rule in situations like circuits or a wire connected to a battery. A straight wire connected to a battery, you'll find that the current is defined to go out of a positive terminal of a battery and towards the negative terminal of the battery. So if you point your right hand with the thumb pointing down in this direction from X to Y, that's the direction of the current, you'll find that your fingers are curling clockwise So you'll draw concentric circles with their directions shown clockwise. There is also a small detail here. You're required to mind the spacing between the field lines or the flux lines and show that the spacing is increasing away from the wire. That shows that the magnetic field is getting weaker as you go away from the source of the magnetic field, which is the current inside the wire. So what happens if you reverse the battery? The current goes down, going from Y to X. So it's upwards in this case. So you would point your thumb upwards. You'll find that your fingers are curling anti-clockwise. So the arrows would be in the opposite direction. And still you mind the distance or the separation between the flux lines, showing that the field is getting weaker away from the wire. So basically, if you reverse the current in a conductor, you reverse the direction of the magnetic field. If the conductor is a straight wire, then the magnetic field is concentric circles around the wire. By the way, the magnetic field is not just in the middle section of the wire, it's all along the wire. It's not just in this area. So you would have a cylindrical magnetic field around a straight wire. Okay, so let's move on to the solenoid and how to find the magnetic field of the solenoid. Basically, a solenoid would have a magnetic field very similar to the magnetic field of a bar magnet, but it's a little bit elongated, and you can actually see the magnetic field line or flux lines inside the solenoid. For bar magnet, you cannot see the magnetic field inside the bar magnet because it's solid, but in a solenoid, you can actually throw some iron fillings in there, and it would take the shape of the magnetic field or the flux inside the solenoid. So let's go and see how the current flows. So basically, the current is going in this direction. It's going up from behind and coming out of the page from the top and into the page from the bottom. So if you curl your hand in the direction of the current, you will find that the magnetic field will be pointing towards the right. So the direction is out of the right side and into the left side. But how can you determine the north pole and the south pole of the solenoid? That's very easy. If you remember, from a bar magnet, the magnetic field is always pointing away from the north pole and into the south pole. So the right side where the magnetic field is going out of the solenoid is the north pole of the solenoid, and the other side is the south pole of the solenoid. So what happens again if you reverse the current? By reversing the battery, the current here is going into the page from the top and out of the page from the bottom. So if you curl your hands in the direction of the current, you'll find that the thumb is pointing to the left in this situation. So going out of the solenoid from the left side and into the solenoid from the right side. So you have a south pole on the right and a north pole on the left. So, and that's how you use the right hand grip rule to identify the direction of the magnetic field or the current inside a solenoid or a straight wire. Now we come to a certain difficulty when dealing with 3D images. In 3D dimensions, you can draw a simple right and left by drawing horizontal axes. So a horizontal arrow can point simply right and left. A vertical axis would point simply up and down, or up the page or down the page. If there is an inclined arrow or axis towards the top of the page, that means that it's going into the page. If there is an arrow pointing inclined towards the bottom of the page, that's out of the page. So basically you have two examples here. On the left here you have a current coming out of the page, So you would point the thumb of your right hand out of the page. You'll find that your fingers are curling anti-clockwise. So you would draw concentric circles around this wire pointing anti-clockwise or counterclockwise. If you have a current which is going into the page, you'd point your thumb into the page and you'll find that your fingers are curling clockwise. So you draw concentric circles pointing clockwise. Also keep in mind the spacing between the field lines or the flux lines. They must always be increasing.
If you like this video, please like and subscribe to the channel so you don't miss any more videos on electricity and physics in general. Thank you, and see you in the next video.